Okay, we we started talking about this important architecture, um, neural network architecture called convolutional neural network or ConvNets, and we discussed about some fundamental operations like convolution, some basic stuff about this type of architecture. I'm planning to talk about some other aspect of convolutional neural networks to understand, to give you an idea also from the architecture side of thing, and some also other detail, some variations of type of kernels or some other operator is typically used within this kind of architecture. But from the architecture point of view, you can again, it's a layered kind of architecture, and there might be different definition or preference what is called a layer in convolutional neural network. But this is one view, this is another view, and the difference is that you have here the input, right? So you start from input, and you can again imagine this is an image, so has a grid-like structure, has a height, width, and depth, right? So for colored image, like so for example, for C410 is 30 to 3, right? Width, height, and depth. Okay, so this is the input, and then it goes to a convolutional layer, which has some subcomponents, right? So it has some a stage, you could call it a stage. The first one is convolutional stage, which does this convolution operation that we discussed. And then this convolution, if you remember, when we do this convolution, it produces a output tensor or output channels, right? So you get some activation, and then you pass it to some non-linearity. And we discussed about why we need non-linearity way before when we were talking about fully connected neural network, right? And why we need non-linearity, because of we need to learn this non-linear aspect of data. Otherwise, if we don't have this, everything stays linear. And then we have a pooling stage that we will talk today, why it is needed and what it does. But all of these three typically is called a convolution layer. Some other view could consider each of these stages as a layer. So convolution layer, nonlinearity layer, pooling layer. This is also an alternative view, but this the difference is that if you think about it at the abstract level, with this definition on the left-hand side, you at each layer, so each layer produces a tensor. So here you have a tensor like this, and then as a result of this convolution, you also get a tensor of a size, typically different size, right? And you go to the next layer, each layer produces a tensor. But here, for example, not all layers produce a tensor. Convolution does, but for example, the other layers do not. And that's why this definition of the left-hand side is preferred from the representation perspective. But basically, what do you want to call as a layer? So this is useful to think about designing neural network, what do you want to call a layer. And basically, this is a contrast between what we have had in fully connected layer, right? This was a kind of fully connected network that we had, and this is a typically perspective for convolutional neural network. And this is, for example, input, and at each layer you produce a tensor like this until you go to the end. So each tensor, you see that it has a width, height, and a depth. And at the end, you need to produce basically what you want to predict, right? So you show this network input image, for example. What you want to predict is a label for this image. And the size of this depends on the number of classes you have in your model, right? So for example, for C410, since you have 10 classes, this is of 10 size, right? So this is, you can think about it, 1, 10 tensor of this size, right? So it has a depth of 10. So each represent basically the activation for each class, and you can pass this through a softmax to get the probability. So these are typically called logits, and then you can pass it through a softmax to get probabilities with the same size, right? We discussed about this transformation. But this is basically, if you want to contrast fully connected network with convolutional neural network, this is the way how you can think about it. So every layer is a simple transformation from a 3D kind of input to, again, 3D output. And each transformation obviously should be differentiable. You can think about each of these as a transformation from one input to another, from input to output, right? And each could be think about as a function that transforms this input to the output. And so basically, if you think about this again, if you have this view, not all layers have parameters, right? So for example, convolutional layers have parameters, right? The parameters are inside the kernel that you do the convolution operator. But for example, ReLU doesn't have parameter. It has hyperparameter, but it doesn't have parameter the way how kernel works, right? ReLU is a function, right? But if you define the layer as this, a conv layer comprising of ConvNet, nonlinearity, and pooling, like each layer has parameters, right? And that's the difference. If you want to have this preference that every layer should have some parameters to be learned, and that's why this view might be preferred. That's the difference. Any question about this? And we talk about this local connectivity that each neurons, right? So each of these is again a neuron inside this 3D volume that is locally connected. Instead of connected to the whole image, it's locally connected to only part of the input, right? And this is like the input, the image that we are talking about, but general could be since down the architecture, down the network, like this could be from this volume to this volume, right? Not necessarily from input to output. So basically, you have this local connectivity between neurons, and the receptive field of this neuron is local, right? So in this case, for example, this is the size of CFAR10 in this case. So it has 32 by 32 depth of 3 for RGB for CFAR10. And in this case, if we consider a filter size of 5 by 5, right, this is what we talk about, right? So each of these is basically parameters to be learned. This is the kernel size, right? So and then since we have a depth of 3, we need 3 of these kernels, right? So in total, we need 75 weights plus 1 bias parameters to learn. And if you think about it, right, so the important thing here is to remember is that at the again, think about width, height, and depth. For width and height, we move the kernel throughout the input width and height, right? So again, going back to what we discussed earlier, right? So we move the kernel from here to here and then here. So we have this local property when we move this kernel around. But if the input has depth of 3, we need 3 kernels. If that has 20, depth of 20, we need 20 kernels, right? So to the depth, if you can think about it, for the depth, we don't have this local connectivity. Is fully connected in that sense, right? So we have this local connectivity for the height and width, but not to the depth. So depending on the depth, we need that many number of kernels. Right. So this example, for example, give you this, talk about this. So you have input of this size. So for example, imagine that you're in the middle of your architecture, then you have a tensor of this size, right, as your input. So you produce a volume of 16 by 16 to the depth 20. Then you want to, for example, use of kernel size of 3 by 3, but then you need to have 20 of them to convolve to produce the output, right? So this differentiating this basically gives you a better understanding of what's going on during the into the network and how these activations are being produced. So basically at the abstract level, you can think about this, the difference between fully connected and convolution net is that this ConvNet provides some locality aspect, and that's why and we discuss about the benefit of this. And once you learn this kernel, this is, for example, how they might look like, right? So they learn about different features, right? So see the difference, for example, between this and this kernel. right? So they learn different features from your input, and this is how they generalize basically, and how they work. We discuss about the connection between these kernels and features. Okay, some more operator that we need to talk about. For example, max pooling also is important because it provides invariance to translation, and it's very easy, right? So basically, or let's call it pooling, because we have different pooling operator. Max pooling is one instance of such pooling, and pooling is a way that to summarize the data, right? So for example, consider this. So for example here, for producing this guy, the receptive field is 3. You look at this, and this. You take the maximum out of this, right? So max pooling is that you look at your receptive field, the neurons in your receptive fields, you bring up the maximum one. This is the definition of max pooling. Again, max pooling is only one instance of pooling. You might have average pooling that take the average of these activations, right? Yeah, you could define weighted average as well. You have different type of pooling, but max pooling is more popular because it has some properties like invariance to translation. So for example, in this case, if an invariance to translation means that if you translate your input, how this affect your output, okay? And let's start by this and consider that, and this is your input, and we translate it to the right, so meaning that we put here, this one here, right? So we have a new value, 0.3 here, that came from here. And this guy is here now, this guy is here, this guy is here, this guy went out of the picture, right? And this is the new output that has generated, and compare it with the previous output, okay? We translated the input, and if you think about translation, meaning that every single value in your input has changed, right? So not equal, not equal, not equal, not equal. So your input has totally changed, but your output, actually half of the output are the same. So these two guys are the same as these two guys, right? And that's the property you want to have. So once you change your input, you want to get some invariances by this change, and in this case is a translation, right? When you shift your input like to the left or right, you get similar thing, or at least not all your output changes. And this gives rise to this property that, like, for example, it shouldn't matter whether in your image cat is here or here, to the left or to the right, should identify this as a cat. Or when you have a face, it shouldn't matter, like, where exactly the eyes are located, right? So it could be more distant, a little bit less distant, but as long as you find your detector, your network finds that there exist two eyes, So this is a human face, for example. It's a face law in general, right? So you get these sort of properties out of ConvNets, or other features that a face or a cat or a dog has, right? So you get these sort of properties which are useful for prediction.
I had a question about the pooling strategy. Maybe I'm not understanding this. I was thinking that it was a particular node would select the maximum value in its receptive field for this given strategy. Is that the strategy?
Exactly. So
because there's this one node where it doesn't look like it. Maybe it's just a typo.
Which one?
It is, so the bottom set of them, the second column, first row. It's 0.1, but I think it should be 0.3. So for the bottom set of them, it's the second column and then the first row.
Second column in the first row. This one, you mean?
I didn't see anything change on the screen.
This one? You don't see anything change?
Above it, yeah, the one node above it.
Here, you mean?
Yeah, okay, I guess I'm thinking about this upside down. But yeah,
So basically, for this guy, you need to look at these three, 0.3, 0.1, and 1. So what is the maximum 1? So you put 1 here, right?
Maybe you could change colors because I'm not really following.
Are we seeing the same image, same slide? Maybe.
Max pooling and invariance to translation.
Yeah.
Yeah, it's just that the color, it's all blending together. I guess I wasn't seeing changes on the slide.
Oh, sorry. Let me.
He was basically saying that you look at all the arrows that point to that node and you take the max out of those three. So there's a 0.3, 0.1, and a 1. You take that 1.
Yes, so you have this, and then you have 1, right? So this one is this maximum, right?
Oh, okay. I see what I did. I shifted a decimal in my head.
Yeah, and for this is the same, right? So, and again, like max pooling is one type of pooling. You might have different type of pooling anyway for your for producing output, right? And you can also have defined pooling cross channels. So here was cross cross for one channel, right? It was for one channel, right? You could have also cross channel. So for example, here is your input, and each of these channels basically learn different things, right? Again, these are the learn channel, right? So if you show this image, so it would activate this this unit, right? Because it's more aligned to the left, right? In this case, it's more aligned to the right, so it activates another unit, right? So here you have 3 units, right? And each of them associated to different features, right? And these gets activated depending on what image you show this. But if you use max pooling across channels, every time that show any image, right? So either this or this, since you take the max out of this cross channel, you always, this layer, you get activation, right? Doesn't matter this, you show this or that one, you get large response in your pooling unit, right? So pooling unit is, in this case, producing one unit out of these 3 different units that you have at this layer. But basically here we are talking about cross-channel pooling rather than within channel pooling. Which is helpful for getting invariances to learn transformations. Any question about this?
So with this method of cross-channel pooling, it feels like I'm getting, some serious, Athena vibes here with the different, transformations.
No, that's different. That's don't associate it with Athena now. We are talking about the property that you get out of your convolutional neural network, right? So basically, think about this as somehow they are connected, but don't think about Athena for now. Each of these are associated with different the way how features are learned throughout the ConvNets, right? Basically, you want to so think about this that you don't want to learn a different model for the basically the images that are tilted to the left and different model from digits that are tilted to the right. So you want to show them any sort of images, however they tilted or look like, and you have one model for detecting those, right? And you need to design your architecture, and given these invariances that you get for either translation, right, to the left or to the right, or tilting, you can define these and how these invariances could be learned automatically throughout ConvNets by the property that these operators have, right? Like max pooling and convolution. Basically, so what I'm saying that each of these operators provide some properties like invariances which are useful for generalization. And generalization, we mean that however these images, your input is located, you want to detect that. Whether you have like 5 here or 5 here or wherever it is, you want to detect that this is a 5. And these are associated to each channel, right, that you produce. Again, corresponding to this architecture that we have. So each slice out of this is one channel. Okay, so you have multiple channels there in this layer. And we have this view also here, right? So this is basically this is producing one channel. Any other questions? Pooling also have other properties, and that's why we want to have that. Is basically have it has a downsampling effect, right? So, for example, depending how we move this kernel in the input map, right? For example, in this case, this is your input. And you have a channel of size 3, okay? Basically these 3 are different weights that are associated to this kernel, right? And then instead of like moving one, you could move like any numbers, right? And we discussed that earlier, right? Here, like you moved it two to the right. It's called a stride. Basically, you could have a stride of different size. Typically, we discussed a stride of size 1, but in this case, it's a stride of size 2. So if you think about like this link, previously it was here. Basically, it was over here, and now it's over here. What is the difference? 2, and that's a stride 2. This is the way how you can think about it. So this thing, instead of moving one to the right, move 2 to the right. Now it's located here, and now the receptive field of this is here, right? So previously you had how many of these? You have 1, 2, 3, 4, 5, 6. Your input size was 6. Now your input size is 3 as a result of this downsampling, right? Basically, again, you're doing max pooling. 1 is max, 0.2 is max, 0.1 is max, right? So you get this downsampling effect.
Were you drawing? Oh, okay. It just all showed up finally.
So basically, you can think about it that one interpretation of this is that we just throw away these smaller values, which might not be important, right? So in the next layer, we only use these bigger values, like 1, 0.2, 0.1. We got rid of like these small values. This is also one.
Could you explain again what stride is? Sorry, the drawings didn't all show up until like all at once just now.
So the stride is basically you could have a stride of any size, right? So stride basically mean that how large you want to skip to the right, to move to the right or to the left, doesn't matter, right? So in this case, we have a stride 2. The interpretation is that like this guy, for example, this connection is now moved 2 to the right, right? Or you can think about this connection as well. Every connection has moved 2 to the right. Does it make sense? Or basically, if you want to have interpretation, this is also confusing. This guy, we talk about like having this and this. This was a stride 1. So you could have this of a stride 2 here first, then here, right?
I think everyone's having the issue. None of the drawings are showing up on mine.
Really?
Yeah, well, I think the issue, and I think that's the issue we've been having, is that
there might be a delay.
There seems to be a pretty serious delay.
Let me check it. I wish you could say it earlier. Stop sharing. That was a strange. So basically, previously we had this move to was here, and then we moved it here to produce this guy, and we moved it here to produce this guy, right? And as a result, we got these 3 guys. Like imagine for the first two rows, right? And with a stride 2, you can think about this. First, we have here, so you get AW plus B X plus whatever, right? You know how to do it. And then you move this guy, you calculate this second output, which is now CW plus DX plus whatever. So as a result, the output size has changed. So this output channel, the feature map, the other word for it, has changed, right? So this is the way how you can think about this, how this asteroid would work. Is this showing up correctly for you guys?
It is now, thank you.
Yeah.
So the stride here that you just showed is a stride of 2, whereas the original example is a stride of 1, right?
Correct. Yes. Yes.
Okay, that makes more sense to me now.
Yeah, exactly. Because like these are arranged different ways, right? Depends how you want to interpret things. So basically, downsampling, you can think about this as a way to summarize stuff, right? Again, here is your input, and this is the output that is produced, right? Again, if you see the depth is preserved, the depth you had previously for your input 64, and you use 64 number of kernels to go over your input and produce your output. So basically you have the same depth as a result of this, but the size of your output has changed as a result of this pooling, right? This is yet another view. So for example, for kernel max, for kernel of this size, okay, so you look at these 4 values, and really depends how you want to do this max pooling, right? So you take the max, which is 6, is here. Again, for this is 8 is here. For this guy is 3, 4, right? So this is the way how things are done, and with a stride of 2, right? With a stride of 1 would be first here, first, the second, third, right? So the output would be larger. It would be 3 by 3 as a result. Okay. If we would have used a stride 1, the output of this operation, max pooling on this input, particular input, which is a slice, which is this slice, for example, would be of size 3 by 3. Can you follow why this is 3 by 3? Yeah, as a result of stride 1, basically you move this window or kernel right, 1 by 1, and you get smaller or larger output as a result. And the key reason is that you don't want to, you basically, the way how convolution at the architecture work, you start with a large input, your large image, for example. You want to then do this downsampling to create a small output, and then you do classification on top of these a smaller output, something like this. So this is your this thing is not ideal. Go away. how works this? So come on. How can I get rid of this? So you see this, like your input image are of size 256, 256 to 3, right? So this is, for example, one size of input image. And then you have a convolution layer that produce this size of tensor 256, 256, 64. Right, this means that you increased the depth. You use the multiple number of kernels here, right? 64 kernels, and then this is the output as a result of convolution. And then you do pooling of a stride 4 to reduce the size, right? And you see that the depth is remain the same, right, as a result of this operation, but you reduce the size, the width and height of the of your output as a result of this pooling operation. And then you do another convolution plus ReLU, basically convolution plus nonlinearity.
I can help you find a place if you turn on location services. Go to privacy settings, select location services, scroll to Syrian dictation, and allow location access.
That's the way how it works. And then so you do multiple operation, right? Convolution, ReLU, and then pooling. Convolution. So think about that way. Convolution, ReLU does the learn the features, right? And then you do pooling to summarize things to get this property of invariances and everything. And then you do multiple of these, again, convolution, ReLU plus pooling, do multiple of these layers. So if you want to have deeper layer, you obviously you do more of these operations down the line in your architecture until you produce a small output, right? So this is, for example, your output vector, which is of this size. So for example, you have 576 units of the output, and then of this size you can do fully connected layer. Typically, once you have a smaller size of output as a result of multiple layers of convolution and pooling, you produce a nice small tensor. On top of this, then you can do fully connected for classification. So think about this as a feature vector or feature kind of feature maps that you produce, and then you want to do fully connected layer on top of this for doing the classification. So typically the later part of your network in this stage is doing fully connected operation. Basically, is a matrix multiplication similar to what we have in fully connected network. But now we don't have these fully connected stuff here. Here it was mainly convolution, which was a lot more efficient, and we get those properties. So basically, the way how we can think about it, you have a large input, we pass it through multiple layers of convolution and pooling to produce a smaller thing. Then once we have a smaller tensor or smaller units or vector, whatever you want to call it, typically you need to reshape it to a vector of a small size. Then you can do fully connected, you can put a fully connected layer on top of this small vector to do your classification, meaning that to produce these output classes. Obviously, before this, you have a logits of the same size we discussed about it, and then you do softmax on top of this to produce the probability that you want to get. So this is typically how it looks like, and like typically you can think about it as large, you make it a small, and then on top of it you do fully connected thing. This is another view. So your image, you have multiple convolution, combination with ReLU, convolution, ReLU pooling, convolution, ReLU, convolution, ReLU pooling, convolution, ReLU, convolution, ReLU pooling, and then you put fully connected layer on top of this for doing the classification. Does it make sense? This is basically, I mean, there are so many variations in convolutional neural network architecture. There are so many variations of ConvNets, basically. But this is the commonalities between different ConvNet architecture that you find out there. All right, so you have some input, and then depending on the number of kernels that you use, you produce of the output of like different sizes, and then you do ReLU and then pooling to reduce the sizes, right? Compare the sizes, the size reduction that you get as a result of this pooling, downsampling. And then you could do fully connected layer to compute the final score on top of which you want to predict the output layer, output label. And the size of this really depends on the number of the number of classes that you have in your model. For CIFAR10, obviously we have 10 classes, and that's why you have this size. So, and again, the size of these stuff, it really depends on the number of kernels that you use in your architecture, right? So when you define your network in TensorFlow, right, you need to define. So this is the overview architecture, right? You define this layer. If you correspond it with your code in the code also you find in Athena, we have defined different networks, right, for doing classification for CIFAR 100, for example, or MNIST. You see a variation of these operator that has been defined there. Input, conv, ReLU, pool, multiple of them, and then finally you have fully connected layer. And yeah, we talk about this, that some of these layers obviously have parameters associated to them. Some of them, like ReLU, for example, doesn't have any parameter, but does have some hyperparameters. This is also another side. We are going over time, but I would like to finish this and move on to the next topic from next week. You can think about this stride again. The way this is another view, the same thing, but with another view. Basically, previously you have this convolution layer that you produce from the input. You produce the output. You get these Z1 to Z5, and as a result of this pooling or downsampling, You basically don't want to have these in between activation. You only get S1, S2, and S3 as a result. These are the your output units that you produce as a result of this larger stride that you have, right? So here, for example, you have convolution operator that has a stride of 2, for example, right? So previously, for example, if you think about this, now here, so it moved two units to the right, and that's the way how we can interpret it. So this is of a stride 2, and that's why you get a smaller output as a result of this downsampling. And there are some other concepts like zero padding. It is useful when you want to preserve your output size with the same size as your input, because we know as a result of this pooling, you get a smaller size of your output. But if you do this many times, at the end you get to 0, right, as a result of if you do this many times. So you cannot, it avoids you to make the network deeper if you want to do this multiple times. So you want to sometimes add this zero padding, meaning that you add some artificial zeros to your vectors in order to preserve the size of your output. With this, you can get, you can make your network deeper as much as you want. You have other types of connectivity. So convolution, it was something like that, where you have, for example, in this case, you have a kernel size of 2. You have A and B. You move this to the right, right? So you have A, B. You move it 1 to the right, A, B. Produce the output. We know about this is the convolution, how the convolution looks like. But you could have also some other local connection, but this time there is no sharing going on. So here we discussed about parameter sharing previously, that parameters are shared. So basically this A is the same as this A, same as this A, same throughout. But here it is, make sure that you understand the difference between this one and this fully connected way. Fully connected layer, everything was connected to the everything else in the next layer. But here we have this locality feature, but there is no parameter sharing going on. So this parameter is different than this, It's not like convolution. This is basically a local connection, similar to convolution, but there is no parameter sharing is going on here. So every parameter is different, but the connections are still local. Sometimes you need this kind of operator, might be useful depending on the kind of task you want to do. Also, you can consider some partial connectivity between channels too. If you think, so each of these represent one, for example, one input tensor, and the channels are here, right? This is the each of those are different channels. And the x-axis here are the spatial coordinates. You can interpret it, but these are like 3D. You should think about this as 3D because these are tensors, right? Previously, we discussed that these kernels, you move to all of these. So basically, each output channels were connected to all of these inputs, right? So that was the previous. So this one is also connected to this one previously for producing the output. But now you can have an alternative way where you have partial connectivity between different channels. This type of connectivity might be also useful for some task, especially when you want to, for example, preserve computation for producing these feature maps. So there are some properties that you can get out of these partial connectivity between channels. You can think of also other type of convolution which were at some point popular, like tiled convolution. So previously, this is the normal convolution that we have, right? AB, we move it down the line. This is the local connection that we just discussed in previous slide, that there is no sharing going on. But tiled convolution is somewhere in between, where for example, you have A, B here, and then you have A, B here again repeated. So there is a repetition going at each different stage depending on the size of the tile, right? So here, so the size is 2. So basically, you have A, B here, and 2 on the right. You again see A, B again. So it is like a tile that moves. And you see, so as a result, you obviously need to learn less parameters with respect to local connection with no sharing, but more parameters with respect to the traditional convolution that we have. And this, I mean, there are some properties you can think about it, that why sometimes you want to have that. Typically, if you think about this output, for example, for S1, it depends on A and B, right? S2 also depends on A and B. So even these neighbors depends on the same parameters. But sometimes here in this case, these neighbors S1 and S2 depends on different parameters, right? So S1 depends on A and B, S2 depends on C and D, which are different from A and B. So these two neighbors are not correlated in some sense. They are not dependent on the same parameter. This S3 and 4 again as well, but this block is also depends on the same parameters A, B, C, D as this block, right? So it's useful if you want to remove correlation between neighbors of your output with the tile, and with different size of your tile, you can increase from 2 to more sizes, right? So you have a control on the size of your tile in this case. Yeah, let's stop here because I think that was everything you needed to know about convolutional neural network. So now you have somehow an understanding how ConvNet looks like from the architecture perspective. Some of the operator, so it doesn't look strange to you when you deal with this type of models, and especially when you corresponding them with fully connected models that you're familiar with, typical matrix multiplication that we talked about it extensively before, and how they are different and what kind of properties they provide, especially about invariances stuff, parameter sharing, locality aspect, invariances to translation, this kind of thing, and the efficiency, especially in terms of computation and storage. That's a high-level perspective or correspondence or contrast between fully connected neural network, dense neural network, and convolutional neural network. Right, and that's why they are much more popular because with fully connected, you cannot make it deep. Like the model gets so large, you need to store billions of parameters. Even with like relatively shallow network comparing with convolution, you can make it really deep, but relatively much smaller operation and storage that it requires. But again, like if you make it really, really deep, the number of parameters that you need to learn will eventually is also too much, depends on the size, but a lot more efficient, different orders of magnitude comparing with what you could do with fully connected network. Is there any question here? If not, then let's stop here. See you. Good luck.